Hi, my name is Joe, and my dad's a rocket scientist. And in this first episode, you'll learn a little bit about him, his history, where he came from, how he got into science, hear a couple stories, get a little deep on cosmic rays and stuff like that. But this is just sort of a background episode. We'll get into more sort of details of what are detectors and black holes and stuff like that in further episodes. I promise we'll get better as the time goes on and as we get more used to this. Hope you enjoy it. Hope you learn something. And just have a good day. Enjoy. Hello, my name is Joe, and my dad's a rocket scientist. Say hi, Dad.
Hi, Dad.
All right, so
we're going to keep doing this joke every time, right?
And I think that's the plan. That'll be the T-shirt.
There you go.
So I think last time when we left off, we were still sort of going over your history and all the stuff you have been doing. I believe you are already at Goddard,
right?
And we're starting to work on sort of more astrophysics related and sort of detect related projects, right?
Well, right. As I said when I got there, Frank McDonald basically said, how would I like to do X-ray astronomy? And I hadn't ever done any of that, and it sounded like fun because it included shooting off a rocket in 9 months and stuff. So that's how I got into X-ray astronomy. Had to do a lot of quick learning about the sort of things one would study in X-ray astronomy and how the detectors worked. And because in my thesis, my detectors detected charged particles, ones that had an electric charge like electrons and protons and stuff. And X-rays are a little bit different than them, but it's the same idea. They leave a bunch of energy in the detector, and the detector can tell you how much energy was left. And I was lucky enough to be in the X-ray astronomy group at Goddard led by Elihu Bolt, and with two phenomenal technicians, Chuck Glasser and Frank Bursa. And basically, they taught me everything I needed to know about detectors, and Elihu taught me everything I needed to know about science, well, almost everything. And it was just a great collaboration. And at that time, Goddard X-ray Group was building 4 different instruments for flying on satellites, various satellites, and so it was a really amazing time to be there. One of the instruments was called the All-Sky Monitor, and it was a X-ray detector that went on a British satellite, Ariel 5, and as the satellite sort of spun around in the sky, it could detect X-ray sources, pretty bright ones. It wasn't terribly sensitive, but it was one of the first ones of these to be orbited and put in space. And that we started to learn about sources that would all of a sudden flare up out of nothing, and that there was nothing there, meaning it was whatever was there was below detectability. And all of a sudden they might get 1 million times brighter. And what in the heck would that cause that? And the Ariel 5 All-Sky Monitor would catch the bright transients that were either black holes or neutron stars that all of a sudden had a lot of material falling on them or towards them from a star that they were orbiting. So it was a binary system, meaning 2 objects, one a regular star and one either a black hole or a neutron star that have very strong gravity. So they were essentially sucking the atmosphere of the other star onto them.
So I'd always heard about with black holes that they have such amazingly strong gravitational pull that not even light can escape the pull of it. So, but what you're saying is that there's actually, you're able to detect stuff that's sort of shooting out of a black hole? Is that right? Or going into a black hole?
It was the stuff falling in. For a black hole, you were seeing X-rays created by matter that was swirling around and about to fall into a black hole, sort of like water going around your drain in the tub. While it was going around and falling in, it was getting hotter and hotter and hotter and glowing at higher and higher temperatures. And at some point, the temperatures were so bright, tens of or hundreds of millions of degrees, that they glowed in X-rays. And those were the X-rays you would see coming from a black hole. It's really from the vicinity of it. Because once this matter fell within what's called the event horizon, which is the distance away from a black hole that, as you say, no light can escape once it gets inside that radius. So we see the stuff just before it falls inside that radius. And on neutron stars, it was stuff that was either hitting the surface of the neutron star and making a lot of heat and X-rays, or stuff that was channeled by the magnetic field of the neutron star onto the magnetic poles. Just like, the magnets you might have done in high school, a bar magnet, and you'd put the metal filings on a piece of paper and you could see the lines of the magnetic field. Well, these neutron stars some of them are just huge bar magnets like that. And so the matter would get funneled onto the magnetic pole of these neutron stars, and get really hot and glow in X-rays. So that's how we would see them.
Okay, so just going back for a second, black hole is what a black hole is when a star basically has lived its life cycle, it sort of blows up and then implodes on itself, creating this little itty-bitty thing that has an absolutely massive gravity that sucks everything into it, right? Is that approximately correct?
Something like that. What it is large stars, maybe 10 solar masses or bigger, something like that.
And what is our sun? Is that one solar mass?
Yeah, that's what a solar mass means, is the mass of the sun.
Okay, so six times the size of our sun.
Heavier, 6 times more massive,
all right.
Or 10 times more massive, or whatever. And what happens is, as the star is living out its life, it's creating a core at the center of it that's pretty much iron. And at some point, when the fuel is being used up, the core starts to collapse, and that's when you have a supernova explosion. And if the cinder that's left over is about 1.5, 2 times the mass of the sun or less, you end up with a neutron star. But if it's more than that, not even the material just can't stop gravity, and it continues to collapse. And we don't know what it collapses to, because the physics says, there's nothing to stop the collapse. I don't think it goes down to nothing. Something's got to happen in there. But we can't get any information because of this event horizon, this distance away, where inside that distance, no message can get out, no light of any kind can get out. So we don't know what's going on in there. And that radius is about the size of a major city. It's 10 kilometers in diameter. It's not that big, and it weighs, 3, 10, 100 times the mass of the sun. And there's basically 2 types of black holes we observe in X-rays. Ones are like the ones I was just talking about, where it's a star and a collapsed object, a black hole. And that black hole is generally around 10 times the mass of the sun. But at the centers of galaxies, our galaxy and other galaxies, quasars, things like that, they believe, and we've measured it, that there are black holes that are millions or billions of solar masses. And they're what's powering what's called an active galaxy. Matter, they're still sucking matter onto them from their vicinity, and giving off X-rays, and they're the brightest objects, X-ray objects around. So there's sort of 2 kinds of black holes we deal with, ones that are going around regular stars and ones that are at the centers of galaxies.
Okay, and then when you say a neutron star, Is that so? It's after all the atmosphere and everything's burned off of a traditional star. What is there like a
It,
mass or what? I mean, what
yeah,
is a neutron star? Does it
it's
glow? Is it something that
where
you could
it's,
land on?
yeah, you could. You wouldn't last very long, but you could. In that it's something, again, it's about 10 kilometers in diameter, but it only weighs, say, 1.5 times the mass of the sun, which is still incredibly dense. And the inter-neutron nucleon forces, think of it that way, are enough to keep it from collapsing down like a black hole. There's only 1.5 solar masses, and that's enough. It can hold off that much. But if it was much higher than that, it couldn't hold it off, and it'd become a black hole.
I mean,
So
is it literally? Is it like a
a
charcoal briquette, but that's super
yeah,
super
yeah.
dense?
It's this. You can think of it as the cinder that's left over after, a star blows up.
Okay.
That wasn't too big of a star. And mountains on there are maybe 1 millimeter high, things like that.
What, perfectly spherical, you think?
Eventually, because many of them are born spinning, and the centrifugal force has them a little bit out of shape. But as they slow down, that shape becomes more, and the centrifugal force gets less, and they become more and more spherical. So pretty much, yeah, they're a sphere.
Wow, okay. All right, so you were with Elihu, Boltz, and the rest of your Goddard crew.
Yeah, so they had 3 other instruments they were building, one of which I was involved with, and that was the building of detectors that would go on the Hyowon spacecraft. And the Goddard was providing some of the detectors that would measure X-rays in the range of 2,000 electron volts up to 60,000 electron volts. And X-ray astronomers use this. You can think of it as another way of saying something other than wavelength, in that for optical light and stuff, we talk about the wavelength of red light or the wavelength of a certain light. Well, the wavelengths are so short up at X-ray energies, we talk about how much energy the X-rays carry. So this was 2 to 60,000 electron volt detectors. They could detect X-rays in that range. And that if X-rays were much higher energy than that, they'd go through the detector without interacting. And if they were much less than that, they wouldn't make it through into the detectors.
So sort of the detectors have sort of a sweet spot that are customized for a specific wavelength or energy, as you say.
Right. And that depends on how you make the detectors. So for these detectors, they were filled with noble gases. In this case, they were argon. There was an argon detector and 3 xenon detectors. Argon and xenon are elements. They're gases, sort of like neon in the neon signs, but just a different atomic number. And they were such that when X-rays came in, they would knock one of the electrons out of a xenon atom, and that there was a high voltage in the detector that would accelerate the electrons, and they'd bump into others and sort of make a little cascade. And then there was a wire that would collect all that charge that hit the wire. And by measuring how much charge hit the wire, we knew what the energy of the X-ray was. But there's only so much gas in there, and the higher energy X-rays would just go right through. They wouldn't interact with the xenon gas, sort of like, when you have an X-ray of your teeth or something, or your broken arm, they can make it through the tissue, but they don't make it through the bone, because the bone can stop it, but the tissue isn't enough to stop it. And then there's other detectors, such as the ones I got involved with later, that have a crystal called sodium iodide, and that's denser than the gas, so it has better stopping power, and so it can go to higher energies. But the way the thing works is they're not real good at low energy, so they sort of start at 15 kilovolts and go up to 200. And they have when the X-ray goes in there, it knocks out an electron, but that makes the crystal give off a flash of light. And there were special tubes, glass tubes, that could turn that flash of light into a pulse of electricity. And once it's a pulse of electricity, we can measure how much is there and therefore get the energy of the event. So there are
was it the sort of thing that you would have like different sets of these sort of detectors in one big unit to sort of cover the spectrum?
Yeah, it's sort of that way. And on Hyowon, it was that Goddard supplied detectors that covered 2 to 60 keV. Caltech made lower energy detectors. They went from about 1/10 of a keV up to a few keV. And UCSD made detectors that went from about 15 keV up to millions of electron volts, but they did it with 3 different kinds of scintillation detectors, these special crystal ones, and we are all pointed in the same direction. So when the satellite was pointed at a black hole or whatever, you would get X-rays over the whole energy range they covered, and that lets you understand what was going on a lot better than if you just had a much narrower vision of them.
And by understand sort of what you're looking at, is that you're just sort of saying, oh, hey, something happened there? Or are you able to sort of get more information where it's, oh, okay, that whatever we're looking at has oxygen and helium or something like that?
Something like that. The whole idea in astrophysics is to figure out what's going on, what's the physics going on at these various objects. So there's a bunch of different ways you can learn about what's going on. One is you can look at the spectrum, which is the distribution of how many X-rays came in at various different energies. And so there might be more at low energy than high energy. And you would look at this distribution, and then you would go to your physics textbook and say, of all the processes we know that can make X-rays, which ones make a spectrum that looks like this? And from that, you can figure out what's going on, whether it's just a glowing object that's so hot it glows in X-rays, or is it that the particles are bouncing off of each other, creating X-rays, or is it sometimes it's low energy X-rays get wonked by an electron and knocked up to higher energies? All these kind of physical processes you try to figure out, among other ways, by looking at the spectrum. Another way you can look at things is how many came in per second, and how did that change in time? And so you might see ones where all of a sudden they got real bright every 1.24 seconds, maybe. And that would be a pulsar, and that gets you thinking about these neutron stars with all the X-rays pounding down on the magnetic pole, but the thing is spinning around. So sometimes the X-rays are pointed at you and sometimes they aren't, and then they come around and be pointed at you again and again. And therefore you can measure how fast the neutron star is spinning. And you can do other things like look in the spectrum, and at the higher energies, some of these neutron stars with very strong magnetic fields can give you evidence for what the strength of the magnetic field is by looking at the spectrum. And so we measure how strong a magnetic field is on these guys. And then if you have other instruments that make images that can actually take a picture of what's going on there, sometimes, well, first of all, you would find out where on the sky the thing was, and then you can go to Mount Palomar or the Keck telescope, some of these optical ones, and say, is there a star there? And if there is, that's generally, okay, this is a star that has a black hole or a neutron star spinning around it, and that starts to help you understand how much matter might be coming across and what that star would be doing to lose its atmosphere the way it is. In other cases, you look at these guys in the radio or other places, and you can see a jet of material shooting out from the black hole. And that would...
But once again, that's shooting out from, like, before the event horizon.
Yeah, from the vicinity, yes.
Gotcha.
Yes, absolutely. And now you have to figure out, all right, what in the heck's going on there to let matter go squirting out the top of these things. You can sort of think of it that way. And for these supermassive black holes, the ones that are at the centers of galaxies that are maybe 1 million or 1 billion solar masses, these big things, some of them are shooting out this beam, and the beam is incredibly long. It's as long as the galaxy itself, or even bigger. And that means it's been shooting out for a very long time, maybe, I don't know, 1 billion years or something like that, or 1 million years. And so now you got more stuff to try to figure out how in the world is it doing that. And these are, some of these are called quasars, or radio galaxies, because they were initially discovered by radio telescopes. So you can learn all sorts of things, and NASA has just selected a new telescope that will be built over the next 5 or so years that can look at one more property of the X-rays that come in, and it's called polarization. And you may know from your sunglasses, if you have polarized sunglasses, that it cuts down the glare. That just means that the light coming in it's sort of 2 waves is the way we describe a light particle. A photon, it's a bundle of waves, but there's sort of 2 directions, up and sideways to it. And your polarized glasses can eliminate, say, the up and down waves and only see the ones that are horizontal, and that helps knock down the glare. Well, in X-rays, this for the first time really, we'll be able to see how many X-rays coming from a given object have up and down or just sideways polarization. And again, that will help us learn about what's going on at these objects, because the theoreticians have come up with their theories and predictions that, this should have a lot of polarization or not have a lot, this sort of thing. And that's sort of the 4th property of light that we can study. We can study the image of it. We can study the time it comes in. We can study the energy it has. And soon we'll be able to study its polarization, all adding to the information of trying to understand what's going on at these objects.
Now, do you know where that observatory or whatever is going to be built?
Yeah, Marshall Space Flight Center has been selected to build it in cooperation with the Italian scientists. The Italian scientists developed the detector for it, and Marshall is putting together the telescope that the detectors would be at the focus of, and so together it'll go up, and it's a NASA mission that'll go on a satellite that'll go around the Earth at about 500 miles or 500 kilometers, that sort of thing.
Satellite, not a ground-based one.
If you're going to look at X-rays, you got to do it in space, because our atmosphere absolutely stops all X-rays and gamma rays coming in from outer space. You can't even go up on a mountaintop to see them. There's enough air above it to stop the X-rays, and to some extent, we're lucky. I mean, we'd be in big trouble if the atmosphere didn't stop X-rays and gamma rays.
Yeah. Okay. So while you were at Goddard, and they said, "Hey, how would you like to mess around with rockets?" And so you got working on this one project, and I mean, what kind of rocket are we talking? Like a big Delta or Space Shuttle-y kind of rocket, or? Hyowon
was a big satellite. If my memory serves me right, it weighed about 6,000 pounds. And it was launched by an Atlas Centaur. And I was down there for the launch, and it was really sort of amazing in that it had been raining. And so they had delayed the launch for the rain to stop. And then it was all clear, but there was a fishing boat in the impact region where the first stage booster would fall, and they had to get them out of there for safety reasons. And they couldn't get them on the radio. They had all of the Air Force and NASA communications. They couldn't get a hold of this people in the fishing boat. So one of the operators went out, got in his truck, and called them on a CB radio, and he was able to get a hold of them, and they left the area in time. And there were low-hanging clouds at launch. And I remember when the Atlas lit. The whole place turned yellow because it was burning kerosene, and that's the color of it. But it was just an amazing launch. And that went into orbit, and everything went well. And we had a year and a half of data from it before it re-entered and was burned up in the atmosphere.
And so is sort of a year or two, is that sort of the common lifespan of these telescope satellites that go into orbit?
Not anymore. Most of the low Earth orbit ones, as we call it, are put up at about 500 kilometers to start. And they'll stay up there for years. And what brings them down is the activity of the sun. In that the sun has an 11-year cycle of activity when there's lots of sunspots and then not many, and then more, and then not many. And when it's in its active phase, when there are when there's more sunspots, it actually heats our atmosphere a little bit more, and the atmosphere expands. So the drag on the satellites is more during active times than inactive times. And as satellites normally are losing a little bit of altitude all the time, just because there is a tiny amount of drag up where they are from the residual amount of atmosphere. And so once they get down around 400 kilometers or less, then the active sun can really affect them. And that's most of them re-enter during those periods of time. Now, sometimes the sun isn't as active as predicted, such as the last solar maximum, time of maximum activity, wasn't as bright as the previous ones. And so the satellites didn't drop as much. The satellite I was involved with most recently was still in orbit 20 years after its launch. And it's getting low, but it sure hasn't re-entered yet. So they can stay up for a long time. And people try to design it such that it can operate for a long time. But this is a real trade-off, because if you say, I'm going to design it to last 15 years, that means you use much more expensive parts. You do much more testing because you've said you want it to last 15 years, and that makes them very expensive. Whereas if you're smart and you say, oh yeah, it's a 2-year mission, that's our prime mission, we can do everything we said we wanted to in 2 years, but we're going to be smart about it. We're going to design it such that there aren't single point failures, as they call them, where if one thing dies, that kills the whole thing. And so parts are selected not so much as being the super expensive and super tested ones, but ones that we know about and they have a good history. And so the one I was talking about, the Rossi X-ray Timing Explorer, we had a 2-year prime mission. It was designed to last 2 years, and NASA turned it off after 16 years of operation. Yeah, a few things were failing, but it was still collecting data. But there's only so much money in the NASA budget for operating satellites. And so it was about time for the Rossi X-ray Timing Explorer to stop taking money out of that budget and let it be applied to some of the newer satellites. And it's one of the real frustrations, I think, for some of us, that budget for operating satellites hasn't really been expanded a large amount in recent years, when there are just many, many, many satellites that are still working just fine after their prime mission. NASA has a way to deal with this in that every 2 years, all the operating satellites have to say how well they're doing and what they're going to continue doing. And then scientists, a peer review panel, reads all these proposals of what the various satellites say they're going to do. And they give their recommendation or their evaluation of these proposals to headquarters. And, they'll be ranked as to which ones are the best and still doing phenomenal job and great job, this sort of thing. And then NASA headquarters figures out how to fund how many of them they can.
So I guess I'm not clear on what does it take to fund a satellite, because the way I would see it is basically once it's up there, it's self-contained. You're not having to refuel it? Is it the cost for that? Is that just obviously downloading the data or setting up the stream of data from it? There's a cost there, but what other costs are there?
You're right. There's two costs. One is mission operations, the actually operating the satellite by sending up the observing plan for the next week or day, however often they put up the plan, because they don't just look at one object. They go bounce around the sky, so to speak. They rotate around and look at different objects. And depending on the satellite, they might look at 2 or 3 a day. Others might look at 10 or 20 a day. It depends on what their scientific goal was. And then you also, the mission operations people, monitor the telemetry that comes down to say, is everything working fine? Has something happened? And if something's happened, okay, what do we do to fix it and get it going again? And then there's the science operations, which is taking the data, putting it into a national archive in a form that anybody can get a hold of. And there are tools, science software tools, that let you do various analyses that you can get from these archives. And then there are the scientists supporting the scientists who actually analyze all these observations that are being made. So it's supporting scientists, it's supporting the archiving of the data, and it's supporting the operation of the satellite itself.
Wow, okay. So hypothetically, we have a ton of satellites that still work really well, but just because of funding have had to be turned off.
Yeah, and NASA's really pretty good about it in that some of them, they try to keep around because they know they're still doing great things, but they're not the newest and latest things. One of the amazing ones was there's a satellite called Kepler, and it's the one that just stared at one patch of sky to get planets. You may have heard lots of discoveries. Oh, they've discovered 5 new planets, 10 new planets, this sort of thing. It was pretty much Kepler. It was the Kepler data that did that. And it did it for a good time. I forget how long it operated. But 1 or 2 of its gyroscopes died. And so the gyroscopes are what it used to do its pointing, knowing where it's pointed. And so normally you would think, okay, that's it. But the people who were Kepler scientists and engineers were smart enough to say, we figured out a way to operate it with just the gyros we have. Yes, we won't be as super accurate as we were, and we can't go point wherever we want, but they figured out a way they could still get power on the solar panels and still point in a certain direction pretty well. And they could do that for, I think it was like 3 months, and then they'd have to shift the position and look at a different point for 3 months. So they were able to come up with a way to extend their mission, and NASA said, great. They paid for that. And they said it'll only work for like the next 3 years, and then it won't work anymore. And so that's what they did. So sometimes the mission people are pretty smart on how to run, even though through some failures. I remember there was a satellite long ago that had learned how to operate on just one gyro plus a sensor that looked at the sun, and I think a sensor that measured the Earth's magnetic field. Some weird combination. They figured out how to do it so they could still point it where they wanted and get more data. So the scientists associated with these satellites and the engineers and the programmers really are highly creative folks.
And once again, this is Macgyvering, via modem.
Oh yeah, it's all, what can we do? A lot of it is what can we do in software? And how do we change the onboard software that handles the pointing, i.e. which direction it looks? And they get very creative with that.
So you were talking that a key thing for a good satellite is avoiding the single point of failure. Any good stories about single points of failure?
Let's see. It wasn't a single point failure, but when the Compton Gamma Ray Observatory was launched. It was launched by the Shuttle. And they assumed that, they had an antenna for pointing to the ground. And they figured, okay, it's a shuttle launch. We don't deploy the antenna till it's in orbit. It just needs a little spring to once we let it go, it'll go boing and be in the right position. Well, it caught on a little piece of space blanket and didn't move out. But this was the shuttle in those days, and it was launched by the shuttle, so an astronaut could go out and nudge it and get it to come open. And so that could have been a huge failure, and it wasn't. It was very creative. They fixed it. But one of the things with GRO, I think it was GRO, that had 2 tape recorders for holding the data and then dumping it to the ground. And I think after a while, the tape recorder failed. Maybe it was, I forget exactly how it worked, but tape recorders failing was one of the big single point failures for things, and people worried about them a lot. Now we don't use tape recorders at all. Memory, you can get your terabyte flash drive, that's not very big. And so the data is now saved on semiconductors, on flash drives, and then sent to the ground. So you don't worry about them failing anymore. But one of the tests you do is to say, these things are going to be in space. There are cosmic rays, protons, that are going to hit these things. Will they survive? Or how long will they survive? So one of the tests you do is take your memory chip or whatever, your computer chip, and go to an accelerator and blast it with protons and see if it still works. And when it does, then you say, okay, this is a good one. It's qualified to go into space, and we know it'll live, in whatever environment you've put it, whether it's the pretty benign, relatively speaking, environment of low Earth orbit, meaning inside of the Van Allen belts, the radiation belts that sort of protect us also. But if it's going to Jupiter, it's going to have to live through the Jupiter radiation belts, which it means it's going to get blasted a whole lot more. So you have to have electronics that have been tested for much higher dosages of protons than you would for something just in low Earth orbit. So we try to take all these things into account.
Wow. Okay. Yeah, I never realized that. I guess it makes sense that depending on where you're going to send, whether it's a satellite or a probe or something, you really need to test it for that environment.
Absolutely. Now, the worst single point failure, and I guess this wasn't single point recently, was the Hitomi satellite, which was a Japanese mission with a Goddard, a NASA detector on board and stuff. And it was launched in orbit and everything was going fine, but something went a little wonky in the onboard system. And it told, some of the sensors said, we're spinning. And so the idea was, it's not supposed to spin. So the spacecraft on its own sent commands to itself to fire the thrusters to make it stop spinning. Well, the problem was it wasn't spinning. And when they fired the thrusters, it spun it up like mad and it spun itself to death. It got going so fast, it tore the solar panels off of it and everything, and that killed it. So things like that still happen.
Wow, okay. So I remember you telling a story sort of as a kid of you went out to White Plains or something like that and were doing stuff with sounding rockets. Is that right?
Yeah, well, this was the Goddard rocket thing that I first did. It's at White Sands Missile Range, which is on an Army base outside El Paso. And I must admit, I don't remember the name of the Army base. The crazy thing is the sounding rockets are launched by the Navy. So there is a Navy outpost in the middle of the New Mexico desert. And that's where we launched the rockets. And these are the ones I mentioned last time that had a Nike booster and an Araby liquid fuel rocket. And we shot them up they only go up to maybe 100 miles. And with that, they're above the Earth's atmosphere for about 3 or 4 minutes, and they spin around and look at the different objects you're planned, and then it comes back down on parachute, and the whole thing's done in 10 minutes. But it's quite an adventure to be there. And the tower that the rocket is in has floors, mesh floors, that if you want to get at your detector or different parts of the rocket, you can climb up and stand on these floors. But the floors have a cutout in them for the fin of the rocket as it goes up. And there's times when you're straddling that opening and looking down and going, that's a surplus solid fuel booster down there. I sure hope nothing happens. I probably wouldn't feel a thing, but it's fun. It really is. And the Navy guys out there, it was run by a guy named Gunnar Briggs, who he handled all of us and kept us on schedule and doing things right. It was quite an adventure.
Wonderful. Okay, so you're still at Goddard. You're doing your first real big heavy duty rocket satellite launch. That thing goes wonderful. Stays up there for almost 2 years. You said.
Year and a half.
Year and a half. What next? Where do you go from there? How did you end up at UCSD and all that?
Well, it turns out my wife and I decided we just weren't East Coast people. The winters were drab. The summers were humid and air pollution and stuff like that. And my wife basically said she's going to go back to California. If I would like to join her, she think that'd be wonderful. So as part of that collaboration on the Hyowon satellite, I had met Dr. Peterson, who was in charge of the UCSD instrument. And I sort of said, wouldn't you like to hire me out in California? Please, please, please. And he arranged it so that I was hired out there as a research scientist. And we moved out to California. And then I ended up analyzing data both from the detectors I had put together at Goddard and with the UCSD higher energy detectors. And therefore, I did a lot of work on a much broader spectral range than other folks did, energy range. But got into that. And then around a few years later, NASA was had a call for proposals for the next X-ray astronomy satellite, one that would emphasize timing, in that we had seen these pulsars and stuff like that. We wanted to know what was going on at timescales like 1,000th of a second or a fraction of a second. You know, that would have new science in it to help us understand what was going on. So we proposed to build the detectors that would run from 15 to 200 keV, and Goddard Space Flight Center and MIT proposed to do the proportional counters, they were called, that ran from 2 to 60 keV, and also to make one of these all-sky monitors that would spin around and look at the sky and tell us when new sources would show up, but also to monitor how the long-term history of some of these objects in the sky, because that would give us more information. How do they vary on yearly timescales or 6 months or whatever, along with do they vary on 1,000th of a second timescale? And so we proposed for that, and were fortunate enough to be accepted to do it. And so that was my next major thing. Now, I was in charge of this thing. I was what's called a principal investigator, which means I was in charge of the scintillator team and at UCSD. And so we had our design, and we collaborated with an aerospace company for some of the electronics, and we built the thing, and it was launched the second to last day of 1995, and it was wonderful. And there's all sorts of stories about it. You remember it. You were there. In that, for the first attempts at launch from Cape Canaveral, you were there. Mom was there. My parents were there. My brother was there. his kid. It was a big deal. And so the first morning launch attempt, they said, nope, it got down to, what was it, T-minus 10 minutes and holding, and they'd send up a weather balloon just to check out the wind that was up at high altitudes, and the winds were too strong. And so they said, come back tomorrow. Okay, we came back the next day, same thing. Winds are too strong. Okay, one more time. We came back the third time. Sorry, winds are too bad. And we have to change all the radar and stuff at Cape Canaveral because we're launching the SOHO satellite, which was planned in there. So we had to sort of stand down for a week or two while they did that. And so then just your mom and I came out for the next launch. And the fourth try T-minus 10 minutes. Oh, sorry, winds are bad. Came back the fifth day, the fifth time, and they said, T-minus 10 minutes. Oh, winds are fine. Keep going. And we got down all the way to the countdown. We had 3, 2, 1, ignition. We have main engine shut down. And we're going, huh? Isn't there supposed to be smoke and fire and the thing going up in the air? Well, it turns out the oxygen valve on the main engine had frozen shut and didn't open. And the procedures they had in place were very good. They knew exactly what to do because they had 6 solid fuel boosters that were all armed and ready to go for the launch. They didn't push the button to fire those. If they had, it would have gone in the drink and that was it. But the procedures they had they checked, wait, the engines didn't start, shut it down, and everything was saved. And then it took, I don't know, a month or so for them to investigate why it had happened. And they realized, with the humidity and all the stuff in Florida, it had frozen shut. And they had an easy answer for it. They just blew dry nitrogen up the bottom where the valves were and to keep it dry. And so then I had used up all my travel money for going to launches and stuff. Plus, I'm not superstitious. I just know how to read the data. I had been going back to Cape Canaveral on and off for about 6 months, getting our instruments all ready and getting the satellite put on top of the rocket and all the testing they do. When I was in the state of Florida, they never launched a thing. I did not see a single launch. I saw the shuttle go overhead on a landing, but that was about it. However, when I was in California, they launched Deltas, they launched Titans, they had submarine launches of Poseidon missiles. I could read the data. When I'm in Florida, no launches. When I'm in California, plenty of launches. Clearly, it was me. So we stayed in California, and we listened to the launch over a speakerphone, and the launch went just fine. It went perfectly. We got in orbit. Everything was great. And so it was an exciting time from then on, because now the data is coming in every single day. There's multiple sources, and some of the observations are ones we had said we'd like to do. And so it was a very exciting time, along with just seeing how well our instrument worked. And it was working very, very well.
Wow. Yeah. I remember it was.
Yeah. The biggest problem was the launch. And we figured, all right, we're listening to it on speakerphone. We could have watched it on NASA TV, but that was the day Newt Gingrich shut down the U.S. government, and that turned off NASA TV. So that's why we didn't get to watch the launch on real time. We got to watch the film of it, a few days later. And I haven't forgiven Gingrich for that.
Yeah. Wow. All right. Well, so we'll pause your story and get into some sort of current events that are sort of related. Earlier you were saying that your satellite, this satellite that we just talked about, it's still up there, but it had a 16-plus year sort of active cycle, and then a lot of other older satellites have sort of shorter cycles. This week...
And some longer, but yeah.
This week, what was it? Was it Cassini?
Yep. Cassini did its fiery dive into Saturn and was burned up. Like it not re-entered, it entered the atmosphere of Saturn, whistling along at, 70,000 miles an hour, or however fast it was going, and it burned up. But this was after a long and illustrious career at Saturn.
And so Cassini was basically launched primarily just to study Saturn, right? It wasn't one of these that sort of bebopped through planet to planet to planet.
Right. It was specifically two things: to go to Saturn and to make all great observations. And it also carried a European probe called Huygens, I don't know how to pronounce its name. And it was a lander, and it went and landed on Titan, the largest moon there of Saturn. And it lasted for about an hour on the surface before it died, and took some amazing pictures, and they learned a ton about Titan from that. But just the 300 orbits or so that Cassini made around Saturn let it pass by many of the moons of Saturn and get these great images of the moons of Saturn. So, some of the more fantastic things, ice plumes shooting out of one of these into the air. Another one where they discovered a very thin oxygen atmosphere. Titan having lakes, but of liquid methane on them. This other one they think has a lake, is all liquid under a crust. Just amazing pictures.
So I still can't really fathom the navigational aspect of being able to orbit Saturn, where we know it has rings, we know its rings have rings, and Saturn has what, 20 some odd moons?
60.
Okay, there you go. 60 moons, and
the smallest one is a couple miles in diameter. So,
and it's how in the world are we able to navigate that well without having,
without bumping into something?
And this thing was launched years ago.
Well, think of it as how to get to Saturn. It was launched towards Venus, and it went and whipped around Venus two times, to get even more speed added to it. This is a way of not having to use the biggest darn rocket around to launch it. You can use a less expensive, they're still pretty darn expensive, rocket, and go down to Venus, whip around it a few times, sort of slingshot around. It even slingshot past the Earth, came with, 700 miles of Earth or something like that, and then off to Saturn. It took it a while to get there. I think it was, launched in 97 and didn't get there till 2003 or something like that. And it had to work the whole time. I mean, you couldn't have they didn't turn it on that much, but they had it in what's called a safe hold or a cruise situation where, they're keeping everything at the temperatures they're supposed to be, but they're not constantly taking pictures or anything. And then they got there, and they had a fuel tank on board, which let them use the thrusters to do slight changes to the orbit around Saturn. So that let them go over and get the right passage past the various moons, of checking out the rings. And at its very last few days, since April or something like that, it was running around inside the closest ring of Saturn to make really close-up pictures. And the pictures from Cassini are just amazing. And what we've learned from Cassini about moons and about Saturn is just a great tribute to the people who built that thing, and it worked for so long.
Yeah, that's so amazing. And all right.
Now, one of the things to remember is, since it's at Saturn, it's pretty far from the sun. So you can't use solar panels to make all your power. They just have to be too huge, and you couldn't do it. So it's powered by what's called a radioactive thermoelectric generator. basically it's 30 pounds of plutonium, radioactive plutonium in there that generates a lot of heat, and that heat gets turned into electricity for running the satellite. And so that's how they did it. And that's how all the probes that go to beyond Mars are powered, is with these radioactive thermal generators.
And so was it the reason that it ended its lifespan, was it had used up most of that fuel, or?
It had used up every bit of the fuel for the thrusters.
Okay.
That let it change its direction. And they specifically used the last bit of fuel to make it enter Saturn. They didn't want to leave it in orbit where it might have run into one of the moons, and they didn't want to have any contamination of the moons from Cassini. In that I'm sure they did everything they could to keep Cassini as clean as they could when it was on the ground, when it comes to fingerprints and other biological contaminants, but it still probably had some on it. So instead of leaving it in orbit, they specifically had it dive into Saturn and get burned up totally, and then any of that contamination would just be totally burned up. It wouldn't survive the fiery death.
Including the plutonium?
Yeah, the plutonium.
Or did we just nuke Saturn? Is that what you're saying?
No, well, the plutonium, individual atoms of plutonium oxide, probably the nucleus, they survive, but they're scattered all over the place and didn't add much to what's there. Saturn is so huge, it would be diluted just tremendously. So I don't think we nuked Saturn.
Hey, so does Saturn have Saturn's a gas planet, right?
Right, exactly.
Does it have any kind of like an actual surface that one could hypothetically walk on, taking away, realities of gravity and temperature and all that sort of stuff?
Pressure and stuff.
Right.
I don't know for sure, but I believe it probably has a solid core somewhere deep down inside of it. I don't know for sure, but that would make sense. But it's not something you would walk on. I mean, the pressure of that atmosphere would just crush anything.
Neat. All right. Well, good to know. So note to self: don't go strolling on Saturn.
Or any neutron stars.
Or any neutron stars or black holes. Hey, well, what's your just one last thing before we call it quits? Talking about black holes. What was that Matthew McConaughey movie with the black hole? Was that Interstellar?
Interstellar.
What thoughts on that?
Is this the one where he went through a black hole wormhole?
That was one wormhole thing.
No,
Science
fiction. A lot. It's pretty much science fiction in my mind, mainly because getting to the black hole, at some point when you're outside the horizon, gravity, if you remember your equations from college, depends on how far away you are. And it gets stronger and stronger as you get closer and closer. Well, at some point, gravity on your feet will be significantly greater than gravity on your head. And you might get stretched into like spaghetti before you got there. So I don't think it's real.
Wow. So basically
practical.
like you'd have, 200 G's at your feet and 20 G's by your head. Like there's there's a significant in that small period, that small dimension.
Yeah, I don't remember the numbers, but it was much larger than that, like 1,000,000 times more on your feet than your head. But I don't remember. I haven't worked those numbers out myself. I just remember hearing about them.
Sound healthy.
Some of the theoreticians talk about molecules becoming more spaghetti-like and stuff, but I have no confirmation of that.
All right. Well, Pop, thank you for another nice chat. I hope to talk with you more, and I appreciate it.
Oh, well, I think this is fun, and we'll keep doing it.
All right. Thank you.
Thank you.